So Coulomb, another genius Frenchman who's a genius chemist. You know, I'm not saying you have to be French to be a great chemist, but it certainly helps. Anyway, so he noticed that the greater the two charges were, so if I had a really strong positive charge and a really strong negative charge, obviously the force between them is going to be much greater than if I have a single charge. And if they're really close together, also, I'm going to have a much higher attraction. So that tends to explain why if I drop sodium chloride into the water, this particular interaction of a single bond, a single charge on either side can be overcome by water interacting with them. And you remember water, we just learned, has a partially negative side and a partially positive side. So if you get enough waters surrounding sodium on the partially negative side, and you get enough water surrounding chloride ion with the partially positive side, you get more interactions. You get a higher, more stable interaction than if you did with the single ionic interaction. And if you have more stable interaction, that's going to take place. So basically, you break the ionic bond, and then you replace it with all of these water-ion interactions. And we'll learn about that in chapter 8, I believe, if we get to it. Basically, you're replacing a whole bunch of smaller interactions that all add up to bigger than one ionic interaction. So that's why sodium chloride is soluble in water. But if you have something like, I think what we were looking at, iron arsenide, something like that. What was the arsenide ion we were looking at in our lab? I forget the metal that we used to precipitate it. Let's say it was iron. Let's say it was iron 2. I think it might have been iron 2. No, it was silver. Duh. Let's look if it was iron 2. So iron 2 arsenate would be this. 3, 2. So iron 2 would be a total of 6 positive charges, and 2 arsenate ions would be -6. So instead of having +1, -1 interacting with each other, now we have +6 and -6 interacting with each other. That is an incredibly strong ionic bond. And water is not going to be able to break it, because water interactions will not be sufficient to overcome the loss of energy of this particular bond. And so when you're looking at precipitation reactions, basically they're going to happen when you have a cation that has a lot of charges and an anion that has a lot of charges, and they come together and precipitate. Or if you have a really small ion comes together really close to a large negative charge, that also tends not to be terribly soluble. So this sort of explains why some ionic compounds are soluble and some ionic compounds are not. Any questions about that? Because, I mean, you've sort of been asking, like, you know, when you have 4 ions in solution, when we mix 2 ionic solutions together and something precipitates, you're asking, well, how the hell am I supposed to know which one precipitates? Generally, sodium chloride ain't going to precipitate, right? So if the only other possibility is pretty much the one that's going to crash out of solution. All right, let's look at how ionic bonds actually form. We're actually transferring electrons, right? So they're not sharing them, they're transferring them. So if we look at lithium bonding with fluorine, so we know that lithium is in group 1, right? And fluorine's in group 7. So lithium is going to become positively charged, and fluorines are going to become negatively charged. And remember, when we drew these orbital diagrams, it sort of showed where each one of them was. So here's lithium with its 3 electrons. And so it has 2 in the 1s, and so it's full. So the first shell is completely full and stable. And the second shell just has that one 2s1 electron in it. That is the one that moves over and takes its place in fluorine. It physically moves from the lithium, leaving lithium with a full shell. So lithium is happy. It has a full shell. What noble gas does lithium now look like? Lithium's taken on a noble gas configuration. What does it look like?
Helium?
Exactly, yeah. It just has one S2. That's helium. And on the other hand, fluorine had a full shell, one, and it's filled 2s, and it's got room for one more electron in 2p. So if that is -1, 0, +1, it has room for one electron in the +1 orbital of the p subshell, room for one more. And so we know first one in is going to be pointed up, second one in, which is the one it stole from lithium, is going to be pointed down. So now it also has a noble gas configuration. What does it look like?
Neon?
Yes, it looked very good. Yeah, now it looks like neon. So it has the same number of electrons as neon and organized in the same way. So even though neon is neutral and fluorine now is negatively charged, they have the same electron configuration. And so they're both in their nirvana happy place. And so this is going to be different than when we see electrons shared between atoms. This is much easier. This is one atom just gets jacked from one element and given to another one, and we can see where they go. This is the valence electron for lithium, and these are the valence electrons for fluorine. Remember, valence electrons are all the electrons in the outermost shell. Lithium just has one. Fluorine has 7, right? It's got 2 in the S and 5 P's for a total of 7. All right. And we'll get down to what these Lewis electron dots are in a minute. The Lewis electron dots, if you remember them from high school, basically we just give a dot for each one of the valence electrons it has. So lithium just has 1 dot because it only has 1 valence electron, and fluorine has 7. And you see when fluorine becomes charged, it now has 8. And everybody wants 8 valence electrons if they can. If they're larger, lithium actually doesn't care about getting 8 electrons because it only wants to get to helium, and helium only has 2. So if you're really small, you just want to fill the first shell. But as you get bigger, you want to fill the second one, then you want to fill the third, then you want to fill the fourth. Lithium was only interested in filling up the first one. So let's look at some of the properties of ionic compounds. And you've seen some of them. Sorry. All right, good. Ionic compounds tend to be solids. And we saw that when we looked at sodium chloride, magnesium chloride, and aluminum chloride. They tend to be hard crystals and getting softer and softer as the electronegativity difference got smaller and smaller. Ionic compounds tend to be hard, rigid, brittle. They're not malleable like metals. You can't bend ionic compounds or shape them. Remember, we talked yesterday, we could take like a grain of salt in your fingernail and press it down, it's just going to shatter. You're not going to shape it to your fingernail. Ionic compounds don't conduct electricity when they're a solid. Why is that? You probably just read it. It's right there. Electricity means moving electrons. So if electrons ain't moving, there's no electricity. So ionic compounds can conduct electricity when they're mobile, when those when those charged ions are mobile. And they're charged and mobile when they're in liquid, when they're solubilized in water. That's why salt water can conduct electricity much, much better than regular water, than just pure water. And if you melt them, if they melt at a very high melting point, but for instance, I think sodium chloride was like around 800 degrees. So if you heat it to 800 degrees, it becomes a liquid and it will conduct electricity. Here's some of the melting and boiling points of the compounds. And this also sort of is a indication of Coulomb's law. See if you can spot it here. So notice what happens. Here you've got cesium bromide that melts at 600 degrees, and then magnesium chloride, it melts at 714, and lithium fluoride, it melts at, then we get to magnesium oxide, and look at the jump. The melting point jumps by 2,000 degrees. What's different about cesium bromide, or just look at the one just before it. What's the difference between potassium fluoride and magnesium oxide? I'm just going to wait for an answer. Come on, someone be brave. You say one of them starts with K, the other one starts with M, you know, there's a difference. What's the main difference between those two ionic compounds?
What's the question again? Sorry.
What is the difference? What's the main difference? Let me clear out everything so you can focus on it. What is the main difference between potassium fluoride as an ionic compound and magnesium oxide as an ionic compound? What's the main difference there? There's one main difference.
Solid.
They're both solids.
Boiling melting point.
The boiling.
Yeah, well, yes, the melting point and the boiling point are both much, much higher. I'm trying to see if you can figure out what is it about those two compounds that explains that difference. They're both solids. They both melt at high temperature, but magnesium oxide, it takes another 2,000 degrees to melt it. There's something quite different about it. What do you think it is?
One's hot, one's cold.
One's hot and one's cold.
There's a major.
Fluorine is the most electronegative, so it's easier for it to take potassium's electron.
That explains, that's okay, you're onto something a little bit there. That explains why potassium fluoride melts at a higher temperature than cesium bromide, because the electronegativity difference is greater. And the greater the electronegativity difference, the more ionic it is. And so the harder it is to pull those two things apart. But I just talked about something with Coulomb's law that sort of explains what's been going on here. Because the difference in electronegativity gives us an increase of about 200 degrees in the melting point, but not 2,000 degrees in melting point. That's a big difference. There's something else going on than just electronegativity.
Is it because oxygen needs 2 more electrons?
Yes. What are the charge states of? Damn it! I got something popped up in my. What are the charge states of potassium ion and fluoride?
Was it +1, -1?
Yes, indeed, sir. That is correct. I have K plus and F minus. What about magnesium ion and oxide ion?
+2, -2.
Yes. +2 and -2. And so my charge density has gone up. Instead of just having a +1 and a -1, now I have a +2 and a -2. So they stick together much more strongly. And so the amount of energy it takes to break that, and that's basically what you have to do when you're melting it, or when you're melting it, you have to pull that apart so then they can be mobile. And to boil it, you need to add so much energy that it moves into the gas phase. Well, in order to do that, you need to overcome a lot more strength of the ionic bond. So magnesium oxide is a much, much stronger ionic bond than potassium fluoride does because higher charge. So you can imagine when you have like +3 or +6 and -6, those compounds, like, don't melt for like, many, many thousands of degrees. Good, got that one, excellent. And also relates to how soluble they're going to be. If something melts at a fairly low temperature, it's going to dissolve in water pretty easily. If it melts at a really, really high temperature, that means it takes a lot of energy to break that bond, and water's just not going to be up to the task. Now let's look at the Lewis dots. I said we sort of get into it. So Lewis dots, generally, all they are is just how many valence electrons you have. That's it. And we basically can look very quickly at something and tell by looking at the Lewis dot structure, A, what group is it in, and B, how many bonds is it going to form, okay? So when you do, and this really only works for the main group elements, 1, 2, 3, 4, 5, 6, 7, 8, because when we're dealing with transition metals, remember transition metals have all kinds of bizarre valence structures. They have, they use S and P, and D, orbitals. And so they can move the number of valences they have, anywhere from 2 to 7. But the main group elements, why they're called the main group elements, is because they have the same number of valence electrons all the time. So nitrogen always has 5, it's in group 5. Oxygen's in group 6, always has 6. Chlorine is group 7, always has 7. So that's why they're considered main group elements. We can sort of predict what their chemistry is going to be. So we look at the group number. So to figure out how to draw these, we look at the group number. So nitrogen, group 5, okay. So it has 5 valence electrons. Now, what I really want you to take home from this is it's important to write them in a particular way. So we place one dot at a time on each of the 4 sides. And you're probably asking yourself, why the hell do I do that? I know how to draw dots. So this is why. So I'm going to put my nitrogen here. Then I'm going to, where can I make dots? Where's my dots? There's my dots. Okay, so I go 1. Damn it, where's my dots? Where are my dots at? All right, 1. Ah! I want dots, damn you. Okay. Still not getting dots. What the hell's up with this thing? All right. So 1, 2, 3, 4. What the hell is that? Oh, maybe I want something else. Anyway, can you see I got 1, 2, 3, 4. Oh, there we are. Anyway, here, let me start over again. This thing is giving me a pain. So I got my nitrogen. I go 1, 2, 3, 4. So why do I do that? And then you continue. So I have 5, so I just continue to go around. I put my 5th one there. Okay? So why is it important to do it in that order? Well, we'll find out that nitrogen keeps a lone pair of electrons to itself and makes 1, 2, 3 bonds. If I make carbon has, how many valence electrons does carbon have?
4.
Mm-hmm. So I'm going to draw them. 1, 2, 3, 4. I'm done. How many bonds do you think carbon makes?
4.
4. Let's do oxygen. Oxygen. 1, 2, 3, 4, 5, 6. How many bonds do you think oxygen makes?
2.
2. Yeah. So if you follow that rule, you basically always be able to figure out how many lone pairs. So these are the 2 lone pairs of electrons that oxygen keeps to itself. The other electrons that aren't paired, they go on to form bonds. Same thing with nitrogen. Nitrogen has this lone pair of electrons that it keeps to itself, and the other electrons that are all by themselves, 1, 2, 3, are shared with other elements. And this is why carbon hardly ever keeps electrons to itself and pretty much always makes 4 bonds because it has 4 valence electrons. All right, so let's keep going. So for a metal, total number of dots we put in there is just the number of electrons that it tends to lose. All right, so for iron 2, we would just put 1, 2, and it's going to lose both of them, right? Now for a non-metal, the number of unpaired dots is basically the number of electrons that it's going to gain to form an anion. So remember, these are unpaired. So in other words, when nitrogen forms a anion, oops, there I'm going again. You still there? Can you still hear me?
Yes.
Yeah.
I can hear you.
Oh man, I'm fading in and out again. And every time it drops out, my head gets bigger. It's not a pleasant sight. So when nitrogen forms not a covalent bond, but actually an ionic bond, we can look at it this way. So 1, 2, 3, 4, 5. There's my five electrons. So it keeps these, and it gains electrons to here, here, and here. So that's why it becomes -3, because those are the 3 electrons it's going to gain. It wants to pair everything. Remember, elements want to have full shells. They would like to have their electrons paired, like to have their electrons paired in orbitals, and then filled subshells and filled shells. So what elements don't like to have is unpaired electrons. In fact, unpaired electrons are extremely energetic, extremely reactive. We call them radicals. When you have like a single unpaired electron, like let's give you an example. When you all know what peroxide is, right? Hydrogen peroxide. No one knows what hydrogen peroxide is.
Yeah, it's like a antiseptic, I guess.
Yeah, antiseptic. You've already got some in your bathroom right now. That's the structure of hydrogen peroxide. So each oxygen has 2 pairs, two lone pairs. So what happens is that this bond is broken here. But since they're both oxygens and they pull, they're both very electronegative and both pull on that pair of electrons, they each keep 1. And so what happens is that you get these ions. You get peroxide ions with 1, 2, 3, 4, 5, 6. Oh, wait a minute, 5. Sorry, 5. Let me get rid of that one. That has only 5 electrons, not 6. So if it had 6, it would be, and this pair, oh, let me go back. If it had 6 and that pair, it would be stable. But now it has 7. And so it has this unpaired electron. And an unpaired electron is basically bad news. It's extremely reactive. It goes looking for an electron, and it'll take it from pretty much anybody. So that's why when you pour hydrogen peroxide on like a cut or something, it basically anything it comes into contact, any living thing it basically comes into contact with, it just strips all the electrons from it instantly and kills it. So yeah, basically you don't want unpaired electrons around. They're bad news. So the octet rule, remember, octet rule just says they're, the happy number 8. Everybody wants to have a filled outer shell of 8 electrons, or if you're very small atom, 2. So like, if you're hydrogen or lithium or beryllium, you're really, really small. You just want to fill the helium shell, the first shell, and then you're done. Everybody else wants to fill the second shell with 8. So here's the Lewis dot structures that we're going to be dealing with. Usually we deal with Lewis dot structures mostly for covalent compounds, not so much for the ionic, but as you can see, you can. So here, again, sort of takes that pattern that I told you probably should follow, because it will help you determine how many bonds each one of these things is going to form. So, for instance, with boron, 1, 2, 3, then you're done. You stop. Boron forms 3 bonds and doesn't have any lone pairs. Boron is an exception to the octet rule because it just has these 3 valence electrons, and it just shares those 3. Now, aluminum also has 1, 2, 3. It generally just loses those. So its second shell is completely filled. It just gives those 3 electrons away. As you move over and become more and more non-metallic, now over here, these would be nonmetals, right? These are nonmetals, so they don't give electrons away. Generally, they share them between each other, or they take them from metals. So with carbon, as I showed you, 1, 2, 3, 4, forms 4 bonds, doesn't have a lone pair. Nitrogen has 1, 2, 3 bonds, keeps this lone pair to itself. As I showed you, oxygen generally makes 2 bonds and keeps 2 lone pairs to itself. And fluorine, chlorine, everybody else, all the other halogens form 1 bond and have 3 lone pairs of electrons that they keep to themselves. And notice, just like the number of valence electrons, the charge they tend to make, as you go down a group, they're all the same. So fluorine's Lewis dot structure looks like chlorine's Lewis dot structure, looks like bromines, looks like iodines, they're all the same. Oxygens looks like sulfur, looks like selenium, looks like tellurium, all the same because they're in the same group. They react the same way. They have the same number of valence electrons in the same place, but just in a larger shell. They're the same S&P arrangement, but just instead of shell 2, it's in shell 3, or it's in shell 4, or it's in shell 5. But the arrangement of those electrons is identical, okay? Any questions on the Lewis dot structures so far? It'd be really fun when we start putting them together and making compounds.
What do you mean by lone pairs?
Lone pairs, excellent. Someone, finally. So I'm just nattering and not explaining anything. So a lone pair of electrons is a pair of valence electrons that are not shared. Because you remember, electrons need to be paired. Elements are much more stable when all of its electrons are in pairs in a full shell, and in a full orbital, in a full shell, in a full subshell, and a full shell. So they want electrons to be paired. These electrons are already paired in orbitals. Like for fluorine, it's these paired electrons are in S and P, and it has 1, 2, 3, 4, 5, 6, 7. So this is a pair, this is a pair, this is a pair. It's not going to share paired electrons because they're paired. Don't want to share them. What it wants to do to achieve stability is to stuff another electron here. Then it's another pair, and then it's stable. So if an element has a pair of electrons already already paired in an orbital, it's not going to share them. It's going to keep it to itself, and it's going to share unpaired electrons because it's the unpaired electrons that are unstable. You remember when we were looking at the transition metals, as we were adding more and more and more electrons. At some instances, it moved electrons out of S into P, and from out of P into D, just so we could get either half-filled or fully filled orbitals, because that is more stable. Anytime you can completely fill an orbital or half-fill an orbital, that's more stable than having something empty. So it's much more stable to add one more electron there than it is to pull one of these electrons away and share it with somebody else. So basically, paired electrons do not get shared, okay? Does that make sense?
Yeah, seeing the diagram that we had been using before, that makes much more sense.
Yeah, it all comes back, right? I mean, that's why we kind of spent so much time on looking at those weird S&P and D and F. They actually have meaning for something, and yeah. So it basically shows you if you have electrons paired together in orbitals, that's as stable as you can get. You don't want it. You don't want to. If you disrupt that, it actually increases the energy. It becomes less stable. And every element, everything in the universe wants to achieve more stability. It wants to lose energy and achieve more stability. And you do that by filling the orbitals and pairing everything. And then finally, once you've paired all your orbitals and all your subshells and all your shells, then you're a gas. You've become a noble gas, and you have achieved chemical nirvana. So they're all trying to get to chemical nirvana, and you don't get that way by losing paired electrons and giving them away. You pair unpaired electrons. That's how you get there. But yeah, that's a great question. I should have mentioned that. I'm glad someone brought it up. So I'm going to sort of just introduce this. This is sort of what we'll pick up next week, because we're going to take that information that we gain by drawing our Lewis dot structures. And then so we'll take a Lewis dot structure for this atom and a Lewis dot structure for this atom, maybe a couple of other ones. And we try and figure out how do we put all these things into a molecule. And these are the steps you're going to take. Generally, if you have a whole bunch of atoms, you don't know how they put together. Put the one that has the, oops, let me go back. Put the one that has the lowest electronegativity, and put that in the middle. So for instance, phosphate. We've been talking about phosphate and arsenate. That's P and 4 oxygens. So we're going to draw it like that. Why does phosphorus go in the middle? Well, because there's only one of them. But it has a lower oxidation. It has a lower electronegativity. It tends to want to share electrons more. So it goes in the middle, and the oxygens surround it. So then we add the other elements around it. And we add or subtract electrons as need be if they're forming ions. Now, every time we draw a single bond, we subtract 2 electrons, right? So if this oxygen is 1, 2, 3, 4, 5, 6, every time it forms a bond, so that's 1, and then this would form another one. Basically, those 2 electrons become bonds, and we're just sort of left with its 2 lone pairs. And then what we want to do, if there's like electrons left over, and a lot of times there are, we distribute them around so everybody has 8. So we want everyone to have 8, except for the smaller elements who just want to get the 2. like hydrogen. Those would be Lewis structures with single bonds. If we have multiple bonds, and we'll learn about how to make multiple bonds, we're going to be moving some of these elements actually will have more than 8 electrons. Phosphorus and sulfur are classic examples of elements that have more than 8 electrons. And they can, because they have a third shell with places in the d orbital to stuff extra electrons. So if the central atom still doesn't have 8 electrons, we sort of just move things around and make multiple bonds until it does. Okay, well, let's look at an example. And believe me, we'll go over this more and more. You have to memorize this whole thing tonight. Let's look at, what's the name of this? What will we call this? Someone name this compound for me. You have to do it soon anyway. What do we call it?
Touch.
What do we call this compound?
Nitrogen trifluoride.
Yes, nitrogen trifluoride. It is not ionic, it is covalent. And so we have to say how many atoms there are, because they could form all kinds of weird things. So we say nitrogen, because there's 1, and then trifluoride, because there's 3. Excellent. So which one is a lower negativity? Well, duh, it's going to be nitrogen, because fluorine is the Mac Daddy of electronegativity. So we put nitrogen in the middle. Then we count up the valence electrons. How many valence electrons do they have? Nitrogen's got 5, and fluorine's got 7. So first we just start with drawing single bonds. So we'll just go 1, 2, 3. Each one of those bonds is how many electrons?
2.
2, exactly, 2. And so then, so we add them all up. There's 3 fluorines, so 3 times 7 is 21 electrons. And nitrogen's got 5 for a total of 26. So 26. So we've used up 2, 4, 6. So now we're down to 20. So basically, we distribute then the remaining 20 where they need to go so that everybody has 8. But if you remember your, if you remember what their Lewis structure looked like in the first place, it makes this easier to do. Because if you remember, what did nitrogen look like? Nitrogen had a lone pair, right? 1, 2, 3 bonds. And fluorine had 1, 2, 3, 4, 5, 6, 7, 3 lone pairs and 1 bond. Well, look how, when we distribute them, that's exactly what they look like. So we put 6 here, 6 there, 6 there for a total of 18, and we have 2 left. And remember, any electrons left over, put them in the middle, and look what we wind up with. Fluorine, 3 lone pairs and a bond. Yep, that's what happens. All the fluorines, 3 lone pairs and a bond. Oh, and look what happens with nitrogen. 3 bonds and a lone pair. Just like we would have expected. So even if you don't remember what these look like, follow the example. Make single bonds, then distribute the remaining electrons that are left over from all the total valence electrons. Distribute those around the outside. If there's any left, throw them on the inside. And if you're short, you make double and triple bonds. We'll get to that tomorrow. Okay? Any questions? Hey, baby. Any questions?
Professor,
Yes.
for exam tomorrow, we have to also make sure our significant digit correct, or
Yep.
for lab exam.
You gotta come correct with significant digits, or there'll be severe retribution. Not that severe, really.
Okay, and another question. For lab 4, when I did my experiment, all VH is 7. Since I start until I end, everything is
All of the what?
because there is a question asking if it's OH or the question is in the lab assignment. there is a question. Is acid H plus or B base of a
Yeah.
product or reactant? I got all same, BH7.
So it isn't.
So it's just, I will say this reaction is neutral.
Yep. Yeah. If you did the reaction and the amount of H plus went up, then you created an acid. Acid is a product. If the amount of OH minus went up, then you would have created a base,
Okay.
and the pH would have gone up actually. So
Yeah,
if the
I'm lucky,
pH
like-
stayed neutral and the amount of protons and OH minus was the same, then yeah, it was a neutral reaction.
So I'm lucky.
Yeah, I don't know. Some people might have gotten an acid or base created. I'm not sure. I think that's why the H plus and OH minus concentrations were shown. I've done it like 3 times and I haven't gotten one, but I don't know how many different reactions there are. Any other questions? Everyone wants to, man, it's getting late. Everybody wants to like throw something in their head before recitation tonight. Okay. I'll try and get the test posted at 10. If for some reason I can't get it there till 11, you'll have till 11 on Saturday to finish it, okay?
Okay. Make it easy.
Because the way my computer's been working, I can't guarantee anything. It might just explode. I'm not sure. Anyway, good luck tomorrow. You're all going to do fine, okay? All right.
So
Yes.
the exam is due by 11 on Saturday?
It's due 24 hours after I post it. So for instance, if my laptop explodes and I don't get it going till noon tomorrow, then you'll have until noon on Saturday. But if I actually can get it posted by 10 tomorrow, then it'll be due at 10. It'll be in the announcement. So there'll be an announcement, the test will be attached, and it'll give you, and then there'll also be an assignment that'll tell you exactly when it needs to be submitted, okay? But you'll have 24 hours from the time it's available.
Okay, and can you
That I
email
promise
me,
you.
Can you email me like the slides, or just let me know what slides will be?
The slides are on the Canvas.
Okay.
All the slides are there. And this is a lab exam.
Oh, lab exam. Okay, got it.
Yeah. So all the labs are posted on Canvas too.
Okay.
Is that you, Rick?
Professor.
Yes.
Yeah, I thought
Yes.
so. All right. Thank you, guys. We'll talk to you tomorrow.
Thank you.
Or actually, we won't. I'll be submitting something to you tomorrow. If you have any questions, I mentioned this recitation this afternoon. If you need some clarification on something, no doubt I'm going to post something stupid, so that may not be understood. So let me know. I'll try and straighten it out. But don't ask me for the molar mass of something. You can look that up. All right.